Okay, so let's talk about bipartite matching. Okay. And the general setting is you have these. So a bipartite graph has these two types of nodes, these two types of vertices, and for convenience we'll call them the blue and the red, or the left and the right. Okay. And all the edges go from the left to the right. Okay. So let me show you an example. Okay. And we'll move to a new application. So resource allocation. So you have tasks. So I'll call the tasks in blue. You have 4 tasks, and the resources that you can use to do these tasks, I'll put them in red. Okay, so you have tasks and resources. Let's say you have 5 resources. Okay, and so let me call the tasks T1, T2, T3, T4, and let's call the resources R1, R2, R3, R4, R5. Okay, and now I'm going to introduce the relationships between tasks and resources. Okay, and so basically, each task can be done by some subset of the resources. So, for example, this task 1 can be done by resource 1, 4, or 5. Okay, and task 2 can be done by resource 3 or 5. Okay, and task 3 can be done by resource 1 or 4. And task 4 can be done by 2, 3, or 5. 2, 3, or 5. Okay. So the way this graph can be read is that, this task, so the links, task 1 can be done by resources 1, 4, and 5. Now the goal is to assign tasks to resources, but you have to assign all the tasks, and you cannot use a resource more than once. Okay. So we're asking for a matching that what's called saturates or a complete matching, a matching that saturates the left vertices. So whichever vertices typically that you want to saturate, we put them on the left. Okay. So can we find a matching? So can we find a matching? Okay. So match tasks to resources. Match tasks to resources. Now the idea here is, okay, so let's see if we can do it. And in this particular case, we can. So for example, we can use resource 4 to do task 1. Okay, resource 4 to do task 1. So I'm going to assign task 1 to resource 4. How shall I draw that? Well, let's say I'll draw a red line here. Thick red line. Okay. And now that we have assigned resource 4 to task 1, look, task 3 also needs to use resource 4, but that's now used up. So we can assign task 3 to resource 1. Okay. So here's another thick line. Okay. And now let's do task 4 and 2. So task 2 can use, for example, resource, let's say resource 5 if we wanted to, or let's say resource 3. Okay, and then task 4 has available 2 or 5, so let's say we go with resource 5. Okay. So, how do we represent? Okay, so now we don't usually draw things like this. How do we represent this matching? As a solution on a computer, we would just say T1 is matched to R1. So T1 R1, T2 R3, T2 R3, T3 R1. T1 is matched to R4. T3 is matched to R1, and T4 to R5. Now you will observe, so we say that this is a complete left matching because every task is matched. Every task has a corresponding resource. No resource is used more than once, okay? But not all resources may get used. Okay. Let's do one more example. Okay. Another example. Similar setup. Okay, so 4 tasks. T1, T2, T3, T4. Okay, and you have resources R1, R2, R3, R4, R5. And now let me show you for this example which resources can do which tasks. Okay, so 1 can be done on 1, 3, 4, and 5. So many ways to do task 1. Okay, task 2 can be done on resource 3 and 4. Task 3 can be done on resource 3 and 4. Task 4 can be done on resources 3 and 4. Okay. So there, I've assigned tasks. I mean, I've told you which tasks can be done by which resources, and now pause the video and, solve the same problem. Okay. Solve the problem. Figure out which tasks to assign to which resources so that every task can be done and you don't use resources more than once. And that means that you construct a matching. A matching technically is just a collection of edges. See, these are all edges where, no two edges share the same vertices. Okay. And if you pause the video and are coming back and you failed to find such a matching, I would normally say you're such a bad finder of matchings, but if you failed, you actually tried to do the right thing and failed because it cannot be done. And now let me give you a proof that it cannot be done. Okay. So my proof is very simple. I'm going to look at T2, T3, and T4. So I'm going to look at these guys. Okay. And I'm going to observe that, if you look at T2, T3, and T4, as a collection of 3 vertices, we can look at where do all their edges go. And all their edges go to these 2 vertices, R3 and R4. Okay. And one nice convenient way of referring to this is we say that the neighborhood of T2, 3, and 4 is R3, R4. So all edges from T2, T3, and T4 go to R3, R4. Okay. So we say that the neighborhood of the set of vertices T2, T3, T4 is exactly the set of vertices R3, R4. And you can talk about the neighborhood of one vertex, you can talk about the neighborhood of a set. So the neighborhood of T1 is R1, R3, R4, R5. The neighborhood of T2 is R3, R4. So the neighborhood for just a single vertex is just who am I connected to? Who are my neighbors in this graph? Okay. And if you think about it, a little bit, you'll say, well, so this just means that all the edges from here go to here. So now if I'm going to match these guys can only be matched to the corresponding neighbors of that set. And if there are only 2 members in this set, well, then how am I going to match all 3 of those unless I'm allowed to reuse a resource? So that is exactly the proof that it cannot be done. Okay? There are more tasks than resources that can do those tasks. There are more tasks than resources that can do those tasks. Okay. So if we call this set X, okay, so we have a set X is equal to T1, T2, T3, T2, T3, T2, T3, T4. If this is a set X, okay, then the neighborhood of X is equal to R3, R4, and the size of the neighborhood of X is less than the size of X, and so that means it cannot be done. In some sense, you can think of X as being a witness, as being a subset that can immediately prove to you that you cannot do it. Okay. So this subset proves that there is no matching. We call this subset a left subset, and we call this the neighborhood of that left subset, which happens to be a right subset of the vertices. And so immediately we see that if there's going to be a matching, this condition cannot happen for any left subset. So for any left subset X, it must be that the size of X is less equal to the size of the neighborhood. Because if that's not the case, you just don't have enough for that particular subset, you just don't have enough resources, to spread around, to go around. Okay? Because all those, if in this scenario, all these resources, all these neighbors have to be spread among more, customers, and that's not possible. Okay? This is called Hall's condition. Okay. And what Hall proved, and you can see the proof in the text, it's proved by strong induction. What Hall proved, okay, so this is just a way to, so if this is necessary, if you violate this condition, there is no way to perform the matching. There's no way to allocate the resources to tasks. Now you might wonder, if you satisfy this condition for all subsets, does that mean that there must be a way to perform the matching? And what Hall proved is yes, by strong induction. Hall proved that if this condition, if Hall's condition holds, then there is always a way to match the left completely with right vertices. And that's called Hall's theorem. Now, okay, so let's check, for example, here where we were able to do it. Well, let's look at the neighborhood of, for example, T1, T2. T1, T2. Well, T1 has neighbors R1, R4, R5. So the neighborhood of T1, T2 is R1, R4, R5, R3 is R1, R3, R4, R5. And you see that the size of the neighborhood is at least as large as the size of the original left set. And what Hall's theorem says is that if that's true for any subset on the left, then you have to be able to find a matching. And it can be proved. It's something you can take to the bank. Now, and it's proved in the text by strong induction. So we won't go through the proof. If you're interested, look in the book. Okay. So what we have to do in order to make sure that there is a matching from the left tasks to the right resources is to verify Hall's condition for all subsets on the left. And if it's verified for all subsets on the left, you know there's a matching. Well, the number of subsets on the left is a large number of subsets, so it's hard to verify. So it turns out that almost as useful is a much simpler sort of version of this. Okay, it follows immediately from Hall's condition. If Hall's condition is true, you know there's a matching. There's a much simpler version of this, which we will prove, and that's usually the more useful one. Okay, basically what it says is that, now this is not, so basically what it says is that, when you look at your vertices on the left, so you have your left vertices, and you have your right vertices. Quick question. Can there be fewer right vertices than left if you want a complete matching? Pause 1, 2, answer. If you said no, then you're right, because the subset of all the left vertices will violate Hall's condition. So there have to be at least as many right vertices. Okay. Now, you can look, okay, so now you add some, you add some links, okay, and you want to know, is there guaranteed to be a matching? Okay. A way to assign all the blue to unique reds, okay, such along edges. Okay. And so what you can do is you can look at the minimum degree for a left vertex. Let's call that delta min. Equals minimum degree for left vertex. Okay. And now you can look at the maximum degree of a right vertex. That delta max equals maximum degree for right vertex. And it turns out that if delta min is greater than or equal to delta max, okay, so if the minimum degree for a left vertex is at least as large as the maximum degree for a right vertex, delta min is less than or equal to delta, is greater than or equal to delta max, then Hall's condition is guaranteed. Okay, and we'll show that. It's an argument that's simple enough for us to show right here on the board. Okay. And if Hall's theorem is guaranteed, then you know there's a matching. And one application of this is to Latin squares. You can see the application as an example in the text. Okay, so proof. So if this is true, then Hall's condition is satisfied. And if Hall's condition is satisfied, you know there's a matching that covers the left vertices, that saturates or completes the left vertices. So let's prove this. So here's the picture. Consider any left subset. So you have a left subset X, okay, and a corresponding, so X has edges, okay, X has edges, okay, boom, 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 who knows, okay, and that goes into some right subset. All those edges combined, when you collect up all those vertices, that's the neighborhood of X. Okay, so X goes into the neighborhood of X. And it's possible that there are other edges going into here. What we know is that all these edges go into there, but there might be other edges going into here. So I'll put those as dotted other edges. There might be other edges. Okay. Now, let's look at the number of solid edges, the ones coming out of X. The sum of the degrees of the vertices in X, okay, must equal the number of those solid black edges coming out of X. So sum for the vertices I in X, so the vertices I in X, so the sum of those degrees, okay, equals the solid black edges, leaving, that equals the number of solid black edges leaving X. Okay. And all of those edges going to N of X, but there might be more edges coming into N of X. So that's at most the number of edges going into N of X. Because there might be other edges coming in, but those edges are not coming from X. Okay? And so the total number of edges coming into N of X is exactly the sum of the degrees, because each of those edges contributes 1 to a degree in N of X. So this is exactly the sum of the degrees for all vertices J that are in N of X. It's the sum of their degrees, delta J. Okay. But now this here is at least the size of X times delta min. Because each degree is at least delta min, so the sum of the degrees is at least delta min times the size of X. And this is at most the size of N of X times delta max. Because delta max is the maximum possible value for that degree. Okay. And so if I compare, I see that the size of X delta min is at most the size of N of X delta max, which means that size of X is at most the size of N of X times delta max over delta min. Okay, but delta max over delta min is less equal to 1 because delta max is less equal to delta min. So this is less equal to 1, so this is less equal to N of X. Okay, so let's see what we have proved. We have proved that if the minimum left degree is at least as large as the maximum right degree, then for any subset X, the size of X is at most the size of the neighborhood. And we didn't make any assumptions about which subset you pick. So this holds. The size of X is at most the size of the neighborhood of that subset for any subset X. This means that Hall's condition is satisfied. Hall's theorem says that if Hall's condition is satisfied, there must be a matching which covers all the left vertices, which uses all the left vertices and assigns them uniquely to right vertices. That's the proof. And this is a much more convenient condition to use than Hall's condition. Okay, and you can see the example application to Latin squares in the text. Okay, so what's a Latin square? A Latin square, for example, is, so here's a Latin square. Okay, 1, 2, 3. So this is a 3 by 3 Latin square. 1, 2, 3, 2, 3, 1, 3, 1, 2. So what's going on here? If you look in any row or any column, so in this row, 1, 2, 3 appears. In this column, 1, 2, 3 appears. In this row, 1, 2, 3 appears, and so on. So in every row and every column, it's the case that 1, 2, 3 appears. Okay? And can you generalize this to 1, 2 up to n? So that's called a Latin square. And Latin squares have all kinds of uses, and we can use this version of Hall's theorem or this corollary to Hall's theorem to show that we can always construct Latin squares no matter how big the square. Okay, and you can see that application in the text. We'll move forward.